Hello students, welcome back. Let's resume our discussion in section 3. Previously, we went through 3.1 and 3.2, the definition and some examples of normal subgroups. The next topic is normal equivalence, and this is actually a pretty small topic, not that important by itself for now, but it will become important in section 4. Please recall that the left coset and right coset were associated to left coset relation and right coset relations defined like this. And we proved that both are equivalence relations. Remember that? We did those in lesson 6 when we studied coset and Lagrange theorem. And the left coset and right coset were defined as equivalent classes. And then we could consider the quotient set of all those equivalent classes and so on and so forth. But now, let's apply that to normal subgroups. In that case, there's no reason to distinguish the left coset relation and right coset relation because they're the same. I mean, I'm not saying the relations are the same, the cosets are the same. Left coset and right coset are the same, so end result is the same. So why would anybody bother? So I'm not going to bother either. I'm not going to consider both of them. I'll just consider one of them. And I'm going to consider left coset relation. And I'm not going to call it left coset relation anymore. And I'm not going to specify this L anymore either. And I'll simply call it the normal equivalence. You see, it's an equivalence relation. We proved it in lesson 6. And left versus right, no need to consider that because they're the same. And that's because we are dealing with normal subgroups, so we have to specify normal. And that's why I named it normal equivalence. By the way, excuse me, not I. That's because mathematicians named it normal equivalence. But then again, whether this subgroup N is normal or not, that's important. So N has to be specified. So we call it the normal equivalence modulo N. We denote it like this. The wave notation, tilde notation, and mod N. Recall that this is an equivalence relation, so we have equivalent classes. And consequently, we can consider the set of all equivalence classes, which we call the quotient set, defined like this. Most of the time, not most of the time, excuse me, back in, what is that, Math 3405, I think, the Introduction to Proof class, the quotient set was typically defined as G/, and then we put the tilde expression or equivalence relation here. But in this case, that's given by the normal subgroup N, so specify N there. And that's a quotient set, the set of all cosets of N. Remember, left coset and right coset are the same, so we don't have to consider right coset. They're all the same, so left coset expressions are enough. Now this thing is called quotient set, and it turns out that this quotient set will turn out to be a group if we define a group operation like this, induced from the original group operation in G. So xn times yn is xy times n, where this xy came from the group operation in G. So this is an induced operation. But then again, whether this induced operation is well defined or not is a big deal, because you can take different representatives, not xn, but what about some x star n? Or instead of yn, what about some y tilde n or y hat n, something different? Are you going to still get the same coset? The answer is yes, it'll turn out that way so that this operation is well defined. And also, it turns out this quotient set is a group under this operation. That group is called a factor group. And it beats me why people decide to call it factor group instead of quotient group. because almost everywhere else, the term we use is quotient. Quotient field, quotient space, and things like those. But for groups, we call it factor group for some strange reason. I think the reason is historical. And there's no way changing it now, so you have to just get used to it. The set itself here is called the quotient set. But if we consider the group structure, the induced operation, it is called now factor group. That's something we are going to discuss in section 4. So for now, let's just be satisfied that this is an equivalence relation now, which we called the normal equivalence modulo n. Okay, the next topic, the normality under homomorphism. Let's see. This is what we want to prove. The normality is preserved under homomorphism. This basically extends this. The subgroup structure is preserved under homomorphism, both in forward direction and also in backward direction. So, image of a subgroup is subgroup. The preimage of a subgroup is subgroup. Likewise, normality is also preserved. But then again, things are a little bit different for normality. Because normal subgroup of what? That's important. The normal subgroup of what? That's important. So of what part is important? Let's go back to the definition of the normal subgroup. You see, that's the definition of the normal subgroup here. And then here's a practical criteria. Okay, all right. So we want to check this. But then again, this has to be true for all elements G in the group we are considering. Now, if this G becomes much bigger group, we replace the G by much bigger group, then there are more small g's to consider. So there are more small g's to test whether this belongs to n or not. In other words, there's more chance this may fail. So it's less likely that n is going to stay as normal subgroup if you consider a much bigger group. So n may be a normal subgroup of a certain group G, but it may not be normal for much bigger group, say G prime. Now, if there's any other subgroup between n and G, then yes, it's going to be normal, yeah, because we tested for everything in G, and H is smaller, then yes, that's true. But if you go bigger, that's going to be a different story. That's what we have to consider, because this phi of G is a subgroup of G prime. You see, the homomorphism here is, as a matter of fact, acting like this. Let's put some space here. This is a situation. And this is much bigger. And this one here. And then that one here. So we are not considering green. It can be much bigger. We are considering blue and red only. Okay, let's prove that. Step 1, step 2, step 3. Step 1, we have to prove those as subgroups. But then again, we already did it. We did it here already. This and that. Okay, step 1 already done. Step 2, phi of n is a normal subgroup of phi of G. So this is what we have to prove. So the practical criteria for that is this. For all element y of phi of G and for all element x, oh, this should be y. Let's call this one something else, h. We want h inverse in this image. That's the question, isn't it? Okay, all right. How can I rewrite this? What do you mean by for all h in the image phi of g? Well, arbitrary element of phi of g is a function value, so arbitrary element looks like this. So this h is actually some phi of g. Same here. Arbitrary element here is a function value, so this y should be a phi of some x, phi of n rather. So this thing can be rewritten as phi of g, and then this one is phi of g inverse, and this one is going to be phi of n. So that's what you have to prove. Is there something you can do? You can use the property of the homomorphism to slip this inverse inside and put everything together, and you have phi of g and g inverse. Does it make sense? Indeed, here's the proof. So phi of g, phi of n, and then the conjugation, we can put everything inside, and g inverse belong to capital N because n is normal. Okay, how about the next problem here? What do you want to prove? The preimage is normal, so we want g, arbitrary element of g, and arbitrary image of the preimage. So x and then we want g inverse belong to this preimage. That's a question, isn't it? Did I say that correctly? Okay, all right. I have no problem about g as an arbitrary element of capital G. But this one I'd like to simplify. So x belongs to preimage. What do you mean by that? That means phi of x belong to this n prime. Same with this. The conjugation belong to this preimage means the function value phi of this conjugation belong to n prime. That's what you have to prove. So can you do that? How can you use the property of homomorphism here? Well, looks like we can do it this way. Phi of x, phi of x, this would be phi of g, and then this one is phi of g inverse, but phi preserves inverse, so you can rewrite like this. Now, does it look better? Yes, indeed. We can prove it easily. Use the property of the homomorphism, and use the fact this is normal, then you can prove that the preimage is normal. The conjugation belongs to preimage too. That completes the proof. So normality is preserved under homomorphism, both in the forward direction and the backward direction.